do entropy part 1.
Okay.
Part C.
So entropy 1, number 2. So we found we did A and B because we knew that the processes that weren't isothermal were both adiabatic and reversible. And if something's adiabatic and reversible, it means there's no change in entropy. And so based on that, we were able to find the heat transfer. So we were able to find the heat transfer and the work for the two isothermal processes. And then we want to find the thermal efficiency for the whole power cycle. Well, we know that, so for part C, we want the thermal efficiency, which is equal to 1 minus QC. Actually, let's not use this one because we have the other one. Do we? Yeah, this is a good one to use. So 1 minus QC over QH. Okay, so we know that QH is equal to W plus QC. And so with this, we can get QC for the two isothermal. You know, we have let's see. So we have Q and W for the isothermal processes. Oh, we're given the temperatures, but well, it is reversible, yeah. So you could just use the temperatures if those two reservoirs. Yeah, right. So that's easier, yeah. Right. Well, you know, like for an isothermal, one of the isothermal processes, you have this relationship, and you know that the total Q is equal to the heat coming in minus the heat leaving. And So you might be able to do it with that. But yeah, since it's a reversible process, you know you can just use the maximum. And yeah, I forgot that the temperatures are given. So you know that so this maximum efficiency is 1 minus the cold temperature minus the hot temperature. So that's 1 minus the cold temperature is 350. The hot temperature is 1400, and that's the answer. Because that's the definition of the maximum efficiency is what would be the efficiency going from with those two thermal reservoirs, what would be the efficiency for any reversible power cycle? They all have the same, and this is one of them, so it's got to be. Any other homework questions? Yep. Okay.
I was wondering like why
Do you have it with you? So this one says air at a pressure of, so at the start, so let's say P inlet is 600 kilopascals, and the temperature at the inlet is 330 Kelvin. The diameter of the pipe, so it's going through this pipe with a diameter of 0.012 meters, 1.2 centimeters, and it exits at a pressure of 120 kilopascals and a temperature of 300 K. And the air, we're using the ideal gas model. And it's steady state. Okay, so we want to calculate the VI and VE, the inlet and exit speeds. We want the mass flow rate. It's steady state, so there's just a single one of those. And then C, the rate of entropy production. It seems like the easiest way to do it. Because we know that m dot is equal to the area times the speed divided by the specific volume. And so, we're given everything we need to use the table at the inlet and the exit, so we can just look up that specific volume. So at the inlet, we can use a table to give us VI and SI. And so, right, that's what we're trying to calculate. Oh, we don't know the mass flow rate either. Okay. So the mass, okay, so we know so what do we know? We know we have the control volume entropy balance. For control volumes. So it says the time derivative of the entropy with respect to, the time derivative is equal to the rate of heat coming in divided by the boundary temperature. And it's well insulated, so there's none of that. And then plus m dot times SI minus m dot times SE plus sigma dot. That's zero because it's steady state. That's zero because it's insulated. All right, so we know that we can figure out the inlet and exit entropies because those are, we know that so it's an ideal gas. So instead of just giving entropy values, it's going to give the S zeros. So let's see, we know that, what do we know? So how do we calculate that? So we can start with, let's just start with the TDS equation. So TDS is equal to du plus PDV. This TDS equation I think it's the other one that we want. So dH minus VdP. And then this V is equal to RT over P. So we have TDS is equal to DH minus RT dP over P. Okay, so what's going to, so let's think about this at both of those two locations. Okay, so at the inlet, so we have this TDS is equal to dH minus RT dP over P. And at the inlet, okay, so I'm just trying to be careful here because when you come out with that change of entropy equation that you get from integrating this, that's talking about at a single location. So that's not talking about like the change in entropy from one spot to another spot. Okay. So now when you calculate this, you get, what's the equation? It's like, you get the change in entropy is equal to this is the S0 at temperature 2 minus, well, that all goes away. So the entropy is not changing at those two locations in time, right? At the inlet, it's not changing. At the exit, it's not changing. Okay, yeah, so use the approach where the temperature isn't, well, the temperature isn't changing at all. Okay, yeah, so yeah, let's start just writing down all the stuff we have. I don't think this is going anywhere. Okay, so what do we know? We know okay, so let's say we start with it's steady state, so entropy just isn't changing at any spot. So it's steady state. So at any well, okay, so what do we know we have to use? We know that we're going to use a control volume approach. So let's write out what we know about a control volume. Okay, so we have the entropy balance equation, and we have the first law. So plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. And what can we get rid of? It says, well, it's steady state, so that goes away. I already changed the M dots, the MI and ME dot to M dot. It says it's well insulated, so this goes away. It's a rigid pipe. Its volume isn't changing, so this goes away. Horizontal pipe, so this is 0. We can look up the enthalpy. So a table gives HI and HE. We have the speeds, and so we can use this equation to calculate m dot. We don't have the temperatures. Well, dang it. Okay. Okay. Well, so let's write this out. Well, let's look it up. Anybody have a ideal gas table for air? Or did you do that in your homework? So what we have here is HI plus VI squared over 2 is equal to HE plus VE squared over 2. .330 point what? Okay. Let's multiply. So let's multiply all by 2, get rid of the, so we have 661.68 plus VI squared is equal to, so, and since we're using speeds, let's put this in SI units. 661.68 times 10 to the third plus VI squared is equal to 0.38 times 10 to the third plus VE squared. Okay, so we can calculate, well, we can get a difference in the squares. Yeah, right. So that's sort of, I'm sort of thinking about that same kind of direction. Like we have two equations for two variables. Let's see what we can do. Well, we have two equations for three variables, don't we? The two velocities and the, okay, well, we have this and, oh, and this is equal to both of them. Okay, so this is actually two equations. You know what I mean? Okay, so let's take this. And we know that m dot is equal to the area times the speed at the inlet divided by the specific volume at the inlet, and it's also equal to the same area times the speed at the exit divided by the specific volume at the exit. And we can cancel the A's. And this now is, so this is one equation. This is a second equation. Okay, so what can we say here? Like, so this one tells us that V at the inlet is equal to specific volume at the inlet times the speed at the exit divided by specific volume at the exit. That ideal gas table, does it give this specific volume or we have to calculate that? When what? Okay. When delta S equals 0. Delta S. The density changes in a gas, right? No matter what you do almost. It's only a liquid that. Okay, so what does it give? For, or what variables does it give in the table? Okay. Internal energy. Well, that's all we need is the temperature to calculate. So for here, you might have to use this percent. Okay, so this is an ideal gas. So for an ideal gas, the specific volume is equal to RT over P. And R is about 287. So the specific volume at the inlet is equal to 287 times 330. That's the temperature, divided by the pressure, which is 600 kilopascals. So if we're using SI units, so 600 times 10 to the third pascals. And someone else is going to have to calculate that because I have Nick's calculator now. What? 0.15785. Okay, and that's SI units. And then for the exit, you have 287 times 300, and the pressure is 120 times 10 to the third. So what do you get for that? 0.789. Oh, 0.717. Okay, so so now the speed at the inlet, use this value. It's 0.15785 times, what am I doing here? I guess let's just come up with a number times the, so we're going to have a number times the speed at the exit. Can you tell me what, so just what's 0.15785 divided by 0.717? Okay, so 0.22 times the speed at the exit. Okay, and now we're going to plug that into, so now we're going to plug the expression for the speed at the inlet into equation star. So we get 661.68 plus 0.22 times the speed at the exit all squared is equal to 600.38 plus the speed at the exit squared. What's 0.22 squared? 0.0484. So what's 1 minus 0.0484? 9516 VE squared is equal to 61.30, right? And so what's the speed at the exit? 64.42. Oh, it's slow. .03 meters per second. And now that was V exit. V inlet is 0.22 times that. So what do you get for that? 1.766 meters per second. Okay, and now we can calculate the mass flow rate with either one of those two. So let's see. The area is pi times 0.006 squared. Okay, that's the area. Times the speed, let's do it at the inlet, times 1.766 divided by the specific volume at the inlet, 0.15785. We've rounded everything off to like one significant figure. We might as well keep all 5 of those. Okay, and what do you get for that? Times 10 to the minus third. And what are the units for this? We've been doing everything in SI units, so this is kilograms per second. And now that we have that, okay, so we haven't used entropy at all yet. Now we're going to have to use the control volume entropy balance. So the SDT is equal to Q over T plus Mi dot times Si minus, these are the same, plus sigma dot. And so what do we, the first two go away, yeah. Yeah, it's a pretty small temperature change, so we could assume a constant specific heat for this. Yep. Okay. Yep. Okay, yeah, so let's go back to thinking about, so now we're back stuck on kind of the same thing. So I'll write this as sigma dot is equal to m dot se minus m dot si. Yeah, so let's think back about that TDS equation. So the first time I was thinking about it, I was thinking about a single location changing in time. But let's think about that in terms of like changing in space, you know, like a spatial derivative. So we have TDS is equal to DH minus V dP. And so TDS is equal to so it's equal to DH minus RT P dP over P. And for an ideal gas, H is equal to, or DH, well, H is equal to U plus PV. So H is equal to U plus RT. And so DH is equal to DU plus RDP. And so TDS is equal to DU plus RDT plus RT dP over P. Well, dang it. Okay, and then divide by T, you get DS is equal to DU over T. plus R dt over T minus RT dP over P du, if we're assuming a constant specific heat, is C dt. So that's Cp dt over T plus R dt over T minus RT. Yep, that's good. Okay, so ds is equal to, so now I'm going to write this as quantity Cp plus R, that's a constant, dt over T, minus R dP over P. And you get that the change in S is equal to Cp plus R times natural log of P. We're doing this in space, so this would be, you can think of this as S at the exit minus S at the inlet is equal to this constant times natural log of temperature at the exit divided by temperature at the inlet minus R times the natural log of pressure at the exit over pressure at the inlet. Yep. We could have done that too. The reason I was thinking before that we couldn't do it was because I was thinking of these as only applying to changes in time. But in what way didn't it work? How do you know what the right answer is? Oh, okay. Well, let's go through this and see. Do you still have your answer with you? Okay, let's see if this comes out as the right answer. It better. Oh, okay. Well, you saw a full solution. Oh, okay. Oh, good. Let's do this. That takes the suspense out of it. So SE minus SI is equal to all this. Well, let's choose a value for CP. Anybody? I don't know what look up CP for 300 degrees Kelvin. And that's in SI units. 0.0041. Oh, 1.0041 plus 287 times the natural log of the exit temperature is 300, inlet is 330, minus 287 times the natural log of, and we have, we just need the ratio. So at the exit, we have, we can think of this as just 12 over 60 or 1 over 5.2. All right, like this. 120 over 600. Okay, can someone calculate that? 434.45. Okay, so now we'll go back to this equation, and now we have everything we need. We have the mass flow rate. So well, let's do this one. Okay, so the mass flow rate is 1.265 times 10 to the minus third. Sigma dot is equal to 1.265 times 10 to the minus third times that change in specific entropies, 434.45. And that's it, right? And what do you get for that? 0.549. And the units are joules per Kelvin seconds. Is that the answer? If that's the answer, I'm going to just shit myself. That really is the answer? I just did like a million calculations, and each one had a like 50% probability of me screwing up a negative sign or something. Yeah, let's. Okay, so S exit minus S inlet is equal to S0 at the exit minus S0 at the inlet. And then what's the last term? But then R ln of what? P exit over P inlet. Okay. And yeah, so let's just oh, I got it right here. So the temperature at the exit, at the exit it's 300 degrees Kelvin. These temperatures in Kelvin, yeah, 300. So 2.36. This one is at the inlet, so 330 degrees. 2.46. These are in kilojoules, though. Two 2.46 times 10 to the third. And then minus 287 times the natural log of 0.2. And so what do you get for all this? Mm. Yeah, off by a lot. Oh, but you included these? And you added those in too? Okay.
Oh, it's 461. 461.8. You don't include the times 7. So
If you don't include what?
you don't use
Oh, yeah. Right. Okay, so what's going on there? You may ask yourself. Mm-hmm. It does matter. I think I converted everything to SI units early on because anytime you're going to use speed at all, you want to probably do it in SI units. Okay. I don't remember what assumptions we made to come to this equation. Mhm. It's ideal, and then this we're taking into account the fact that the specific heats are changing. The other one we're not taking that into account. So you'd expect this one to be the accurate one actually, and the other one to be an approximation. But did you say the? Mhm. From everything that occurs to me right now, this would be the way to. This would be the simpler and more accurate way to do it because you're not assuming a small temperature variation. Um, if I think of anything different later, I'll put that on, put a note on D2L. But I would say think of both of those as fine ways to do it. They're both ideal. Okay, both of these are for ideal gases, but the long way that I did also assumed that that C sub P was constant over the temperature range of 30 degrees. Okay, 30 degrees isn't a very big temperature range, but that still does change, you know? And so you would expect to get more accurate results using an approach where you didn't assume that it was constant over the range. Wait, oh no, I just looked in the wrong column. Okay, hold on. No, this is good, everybody. Okay, so no, it has one temperature here and one temperature here, and I skipped all the way over. Okay, so 330 degrees, S sub 0, S0 is 1.80. That's times 10 to the third. And at 300 degrees, it's 1.70. What? Oh, really? Well, that sucks. What if I put in more units, more digits? Okay, 1.7978. No, sorry, that's the that's the first one. 1.7978 times 10 to the third. And then the second one is 1.70203. That's not going to make much difference. Okay. Okay, well, let's call those both fine. Spoiler alert, I won't put a question like this on the test. I mean, I think all these sort of help you sort, like doing hard problems sort of helps you sort through what you know, what you don't know, but that you won't have to do anything with that many steps or that complicated a thought process on the test. Okay, let me say something about isentropic processes. So an isentropic process means that entropy stays constant, and it requires first, your system has no heat transfer with the surroundings. And second, that there are no internal irreversibilities, internally irreversible. And we're doing this for ideal gases only. Okay, so remember, for a general ideal gas, we know that the change in specific entropy is equal to S0 at temperature 2 minus S0 at temperature 1 minus R times the natural log of P2 over P1. If entropy is constant, then this is 0. And so you can go through the algebra of isolating the ratio of P2 over P1. What you get, you can go, it's only a couple steps, but I'm just going to write out sort of the punchline. You get that e to the power of, so that's a fractional power, S0 at T2 over R. And then all of that ugly thing, over e to the power to this fractional power S0 of T1 over R. Is equal to, and over on the other side you have e to the power of natural log of whatever, those cancel out and you just get P2 over P1. Okay. This thing here is called, notice these both have the same form. And this form is called the relative pressure. And so you can think of this as the relative pressure P sub R at the temperature T2. And this one is the relative pressure at the temperature T1. And those relative pressures you can look up in the table. Alternatively, using the ideal gas law, and you can get an expression that says specific volume 2 over specific volume 1 is equal to this ugly thing that's, so R temperature 2 over the relative pressure temperature 2 divided by R temperature 1 divided by the relative pressure at temperature 1. And we're going to give this ugly thing a name too. We're going to call that the relative volume. So this is going to be V sub R at temperature T2. And this is V sub R at temperature T1. And then you can just look up these relative pressures and relative volumes in an ideal gas table. Okay, so let me do an example of a case where this would be useful. Okay, so for example, let's say that we have air at room temperature, so 22 degrees Celsius, and atmospheric pressure, so 1.01 times 10 to the fifth. And then we compress it in a syringe to half its initial volume. And so we're going to find the final pressure in the syringe under two conditions. So first, assuming that the temperature doesn't change. So that's an isothermal process. So how would you expect an isothermal process to happen? So you start with a syringe full of air, you push the plunger down, and if there's no heat transfer between the air inside and the surroundings, what's going to happen to the temperature of the gas inside? It's going to increase. And so for that to stay isothermal, for it to stay at 22 degrees Celsius, you'd need your syringe, the walls of your thing to be copper or something that conducts heat very well, efficiently. And you'd have to do it really slowly and give it time for that temperature for the temperature inside to come back down to room temperature. Okay. So in other words, if you do this isothermally, okay, well, so that's the first case. Energy, so you push it down, and then energy leaves the gas on the inside into the surroundings. The second case is isentropic, and isentropic means, for one thing, it means that we're assuming no internal irreversibilities, but that's not a big assumption in a simple process like this. But the other one is that there's no heat transfer. So this time you push it down. In which case is the temperature going to be higher? Isentropic. For the isothermal case, energy is going to leave to the surroundings. So in which case would you expect the pressure to be higher? Isentropic should have a higher pressure at the end than isothermal. And I'm doing this example partly because there's a physics lab that we do. Maybe you guys have done this lab at some point where you do that and you change the volume and then you go and you see how well the pressure that you measure inside the syringe matches with what you'd expect from the ideal gas law, assuming that it's isothermal. Well, it doesn't match very well. But okay, yeah, I do a similar one in physics too. But those syringes are plastic, which doesn't conduct heat very well. And so, maybe a better model would be that this is an isentropic process, and that the answers that you get for these two ways of thinking about it are pretty different. Okay, let's see what we get. The second one is isentropic. Okay, so for part A, so for this one, we're just saying P1, V1, that's equal to RT. Temperature is the same at state 1 and state 2, and this is equal to P2, V2. And so V2, we're just going to call that 5V1. So you get P1, V1 is equal to 0.5 P2, V1. Cancel the V1s. And so P2 is just twice P1. And so that final pressure is 2.02 times 10 to the 5th pascals. Okay, so that way of doing it is easy. So now let's go isentropic. So this time, we're going to figure out the ratio P2 over P1, and that's equal to the relative pressure at temperature 2 over the relative pressure at temperature 1. This is a little bit of a nuisance because we don't know the temperature at T2. But we do know that, so P1 is 1.01 times 10 to the 5th. The relative pressure at temperature 1 is Okay, so the relative pressure at temperature 1 is 1.3068 in SI units. Now, since the ideal gas table is given in terms of temperatures, it'd be nice if we could express that P2 in terms of temperatures, and can because the ideal gas law. So we know P2 V2 is equal to R P2, and so P2 is equal to, let's see, so we got R T2 over V2. What did I do here? Oh, here's what I want to do. Yeah, I don't want to do that. I want to find, so I want to get that pressure as a function of, yeah, I want to get that pressure as a function of, temperature. Yes, you're right. Okay, so we have this. Let's see, we have P1. Okay, so we know that this is 0.5 V1. We know that P1 V1 is equal to R T1. So we know that V1 is equal to 0.838. And so P2 is equal to R T2 over 1/2 of V1, so that's 0.419. And R is 286.99. So what's 286.99 divided by 0.419? So 684.9 T2. And so now we can re-express this equation, 684.9 T2 over 1.01 times 10 to the 5th is equal to the relative pressure at T2 over 1.3068. And now we're looking for a relationship between the temperature and the relative pressure. Okay. Look for the spot in the table where, if you rearrange this, you get the ratio of T2 over the relative pressure at T2 is equal to 112.839. That happens at a temperature of 390 Kelvin. And the pressure P2 then is equal to 2.65 times 10 to the 5th pascals. got what we expected. In the case of the isentropic process, the pressure and the temperature were both higher than in the isothermal process. Okay, thanks for taking my class. See a lot of you in dynamics and deform next semester. I don't have that. I think I'm going to wait to do those evaluations until I'm more comfortable with this class in a few years, but I'll let you guys know at that time. I'll send it to you in the email or something. Okay.